Hello again. So you've seen the announcement, and you might be wondering what this compiler project is about. Before I talk about the project itself, let's start with some background. I already write code live on Twitch fairly regularly. Every December, in fact. There's an event called the Advent of Code, themed around Christmas, during which one new programming puzzle is released every day in increasing order of difficulty. Usually. There are no restrictions on how to solve those problems, and while there are leaderboards, most people see the event as a challenge rather than a competition. As a result, it is a fantastic resource to hone your programming skills, whether you want to learn a new language, practice one you already know, or want to do something a bit more out there. Some people write their solutions in Minecraft, it's fantastic. They're not paying me to say this, by the way, I donate to them. The challenge I've chosen for myself with this event has been to write all of my code live, as a way to practice speaking in front of a camera, explaining my code to a live audience. I've been doing it for 6-7 years now, and I've always done it in Haskell. And there's two reasons for that. The first is, it's my favorite language. It's one I have the most fun using. But the second is
propaganda.
Or rather, fighting disinformation. Haskell has a reputation for being difficult and impractical, and I strongly disagree. So, by using it to solve practical problems, I'm trying to do my part in popularizing a language that I think is underappreciated. But sometimes, when I'm done, when my Haskell solutions work, when it's getting a bit late into the stream and a bit late at night, I switch the stream to its After Dark version, and I write my solutions in brainfuck. BF, for short, is what we call an esoteric programming language. It's probably the most well-known one. Esoteric programming languages are languages that have not been created to be practical, but for literally any other reason. For fun, as a challenge, or even as an art statement. Famous examples include intercal, a parody language in which please is a keyword, and the compiler will reject your code if you don't use it enough or if you use it too much. Malbolge, a language so complicated to use that its author never wrote a single program with it. It takes several years of research to do anything with it, and most Malbolge programs in existence have been generated by another program rather than written by hand. There is also Shakespeare, a language in which a program is broken in acts and scenes, and each scene, a function, is written in prose to mimic a play. Here's some white space. The only valid characters in that language are space, tab, and new line. There's Piet, of course. We'll get back to it. And finally, last but not least, there's my beloved BF. It is designed to be a minimal language. There are only 8 instructions, and they're each represented with only one character. Hello World, the first program that anyone writes in a new language, looks like this. And I use it to solve Advent of Code problems. I've actually recently written a small introduction to the topic of writing brain in the context of the Advent of Code. If you're interested, link in the description. But there are 2 parts to the challenge of writing brain. There's figuring out how to express the problem I want to solve in a series of very small incremental steps, how I'm going to translate the logic into that language, and there's actually typing it. I find the first one very interesting, but the second, not so much. For instance, this snippet computes the sum of 2 32-bit integers. I have to copy and paste it every time I want to compute the sum of 2 integers because BF doesn't have functions. Now this is multiplication. I wrote it once, which was an interesting challenge, but I would prefer to avoid having to copy-paste it every time I have to multiply things. Which is why I decided, years ago, that I had to find a way to make this easier. At the very least, I needed to find a way to be able to declare snippets. I started very simple, using C macros to pre-process my BF files, allowing me to name and reuse functions, kinda. Side note, I've also tried to define more of a language at the macro level using the Boost preprocessor library. If you know, you know. But that was not enough. So a few years ago, I bit the bullet and I just wrote a very basic compiler. Now I can write functions, I have a rudimentary type checker. The core challenge of figuring out how to solve a problem with BF is still there, but at least things are a bit easier now. And that's how we arrive at this compiler project. It's the logical continuation of everything I've talked about so far. It's a more ambitious live coding project, it's an opportunity to showcase Haskell's strength in a much larger context, and it's a reason for me to go back to an esoteric language that I love but I haven't used in a long time, Piet. So let's talk about Piet, shall we? So, where BF gives us 8 instructions, Piet blesses us with 17. But what's interesting is how those instructions are represented. As mentioned earlier, the source of a Piet program is an image. The interpreter segments it into cuddles, groups of pixels of the same color. It then starts from the one on the top left and moves from one block to the next. Not all groups are treated the same, however. There are 20 colors that are deemed special. All other colors are ignored and treated as if they were white or black depending on implementation. If you're colorblind, I don't know if this is helpful, but those colors are sorted by hue in the usual order of the visible spectrum, from red on the left to violet on the right. But the colors themselves do not encode the instructions, it's the color transitions. For instance, if you move from a light green block to a dark cyan block, that's 2 changes in lightness, 1 change in hue. That's the multiply instruction. And the instruction does not depend on the starting color. Any change that is likewise 2 steps in lightness, 1 step in hue is also a multiply, like from light cyan to dark blue or from regular yellow to light green. Transitions are always in the same direction. For lightness, it's always from light to dark. They just wrap around if needed, which is why taking 2 steps down from regular yellow brings us back to light yellow. From one of those 18 colors to all of the others, there are 17 possible transitions, 17 different changes of hue and lightness, and therefore 17 instructions. Black and white are different, however. They do not encode instructions, but they help guide the interpreter. White blocks can be freely traveled through, while black blocks are walls that will redirect the evaluation. Let's look at a practical example. And for instance, let's look at the one that's been here the whole time. This one. Because, yes, up until this point, every slide in this presentation has been a valid Piet program. If we zoom on it so you can see its structure, you'll notice strips of pixels of our special colors that are in fact sequences of instructions. And to give you an idea of how the interpreter moves through an image, here's the path that it would take at first. Understanding what those instructions do, however, is left as an exercise for the audience. So this is what Piet looks like. You might be wondering now, how are we going to translate Rust-like code into an image like this? And as you know, the answer is a compiler. And while I've described this project as a toy compiler in the announcement video, in fact, in practice, its structure will be very close to the one of a real compiler. Like a real compiler, ours will operate in phases. At first, to parse the source code, we will start with lexical analysis. Our Lexa is going to decompose the program into a series of individual tokens, keywords, operators, literals, identifiers, and so on. From there, we can do syntax analysis. Are those tokens in an order that's meaningful? Are they in an order that's consistent with the grammar of a language? If they are, the output of the second phase will be an AST, an abstract syntax tree, a representation of the structure of the program we passed. On this representation, we can perform semantic analysis, such as name resolution and type checking. Not only does this check the validity of our program, but it also gathers all the information we need to generate the next structure, the intermediate representation, or IR for short. In this form, no matter how complex our program was at first, it is now represented by a long series of elementary instructions with very strict rules. Being very formal and structured, it is the perfect input for our next phase, optimization, that will attempt to rearrange the instructions to avoid unnecessary work. This is where our compiler will diverge from a regular one, however. At this point, a regular one would generate assembly or even machine code directly, something that the computer can execute. Ours, however, is trying to generate an image. So first, we will translate our IR into yet another representation, bytecode. This form is somewhat similar to our previous one. Our code is here yet again represented as a series of elementary instructions. However, where the IR is abstract, this form is concrete. each bytecode instruction directly corresponds to one Piet instruction or to a known pattern of Piet instructions, making it, in essence, a recipe for how to make the image. We have one more phase to go through first, though, which is somewhat similar to the linking phase of a regular compiler. We need to decide how the functions will be arranged in the image and assign a unique address to each of them. But after that, we can just follow the recipe and create an image. And that's it. But before I go, however, there are two quick things I want to address. First, I want to set expectations. When I do my Advent of Code streams, there is a well-defined structure. I solve 1, 2, maybe 3 problems, and all of them are very binary. There is a good answer, and either I find it or I don't. Here, things are going to be less structured. Not all parts of this project will fit neatly in one stream, or even 2. And there isn't necessarily one good answer. I might make choices early on that I will have to revisit later. I can't guarantee that everything will be smooth sailing. I might not be able to be at the same level of structure that you might have come to expect from me so far, and I want that to be very clear. The second thing is the quick channel update. Some of you have been asking why I haven't been uploading since my first video a year and a half ago. And the short answer is personal reasons. Last year was a nightmare. I have 3, 4 drafts open at the moment, and I have not been able to work on them. Things are starting to improve, and I'm really hoping I can get 1, maybe 2 out this year. Thank you for your patience, and stay tuned.